is going to be probably my personal favorite lecture because that subject has been the subject I built my career upon over the last 7 years. This became kind of hot and discovered when I was coming into the field as a graduate student, so it was right there for me in front of my eyes, a whole new field to do great things with in the University of Texas. But before I go on, I just want to apologize for the handouts. Point 4, there is a small typo in point 4. It says superluminous supernova divided into superluminous type 2 and type 1. So it's hydrogen rich and hydrogen poor. I've repeated hydrogen rich twice. So just bear that in mind. But we're going to talk about superluminous supernova. We're going to talk about some of the most rare, exotic, and enigmatic and diverse events that have been discovered in the field of supernova research. And that discovery only occurred a mere 10 years ago, actually, not even 12. A decade ago. So we celebrate 10 years of superluminous supernova discoveries. And it all started at the University of Texas. I was a graduate student in 2008. That's when I got into the University of Texas, a graduate student. Before me, a friend of mine and another graduate student who was working with the same supervisor, Professor Craig Wheeler, Robert Quimby, he used a small robotic telescope that's located in West Texas, the McDonald Observatory, the desert, which automatically scans the sky on a nightly basis, looking for new transients. Now, the key about this project that I'm going to talk about more is that it wasn't as one of those older supernova search projects that were used in the past. In the past, people would be like, okay, let's look at those bright galaxies. It's most likely we will find stars exploding in bright galaxies. So they would select, they were biased, they would select which galaxies to look at to find new supernovae. And they left the rest of the sky untouched. And this is where the genius of this new project came in. It was an unbiased search project. It scanned the sky blindly without pre-selecting bright galaxies whatsoever. And that's why it was the first project that discovered this new type of superluminous supernova, because it happened that those super bright explosions were associated with really dim galaxies, irregular galaxies. So previous surveys did not select those galaxies. They said, oh, those wimpy guys are not going to produce anything interesting. Well, it turns out they did. Nature always surprises you. So that happened in 2004 when a Texas graduate student, which is currently a University of California, San Diego professor, Robert Quimby, used this ROTC telescope, which stands for Robotic Optical Transient Search Experiment. That's what ROTC stands for, in Texas, and discovered this new type of events. Now, what makes this event special, as the word suggests, is that they're superluminous. They're 10 to 100 times more brighter than regular core collapse supernovae. They're even brighter than type 1a supernova. So they're an entirely new category. They're their own thing. They don't fit, they have their own little partner zoo of supernova, supernova zoology. They're a big monster. So the Texas Supernova Search Project, again, key characteristics of it was that it had a large field of view, allowing for a large portion of the sky to be observed simultaneously, not just a small portion of the sky, and it was unbiased. And we like to say, when I was back in Texas, it's a small telescope, but it gave big results. This is the Hobby Everly telescope. It's one of the biggest, actually the third biggest optical telescope in the United States. It's located in West Texas and primarily operated by the University of Texas at Austin. And this is ROTC, the little robotic telescope that discovered the first of these superluminous supernovae. And turns out that that was a very nice and very convenient configuration to have, because we developed, and Robert Quimby was instrumental in that, we developed an automated program. It was all programmed. But as soon as this telescope discovered something new, we immediately triggered the bigger telescope to take more accurate observations, and SPECTRA, which SPECTRA is true, to figure out what's going on, what is the nature of these new superluminous supernova events. And it was by far the most dramatic discovery happened by the Texas Supernova Search Project. And this is a list of the first few events discovered. As you can see, the first one was in 2005, Supernova 2005 AP, exactly 10 years from today, before today. And followed by, so along the way, we got some new kind of funding. So we renamed the program from Texas Supernova Search Project to Roche's Supernova Verification Project, RSVP. And then, past that point, we had the RSVP discoveries, 2008 AES. And this is a paper that I co-authored. This, by the time I actually led the research in this, and I was part of the discovery team for this using Roche and ACT. And it turned out to be, at the time, the brightest supernova ever checked. So we're all very excited. We opened a bottle of champagne because we discovered the brightest supernova in history. So, but that changed. You know, over the last few years, there's more brighter events, even brighter events were discovered. So this is light curves. This is some light curves from basically, again, the evolution of the brightness of the supernovae as a function of time. And of course, it always goes up and down, it reaches a peak. Now, this scale might be confusing you here, so I'm going to very quickly explain what an absolute magnitude is in astrophysics. It's a way to measure brightness. And there's different ways to measure brightness, but this is very convenient for us astrophysicists. And the more negative it is, I know it's counterintuitive, the brighter it is. So minus 21 is brighter than minus 19 in this case. And the difference between one magnitude, going from minus 19 to minus 20, corresponds to about 2.5, 2.5 times difference in luminosity. So it's basically a logarithmic scale. So I'm not going to say anything more about this, but note that all regular supernovae are down here at minus 19 level. And all these guys, you know, they can get all the way to minus 23, minus 22. They're really bright. So as soon as we discovered how bright they were, we're like, what is going on here? These are not gamma ray bursts. These are optical signals. This is nothing like we've seen before. New physics to be discussed. So what are the key observational? Now that we've discovered a bunch of them, actually right now we have of the order of 60 discovered with the onset of all the new high cannons tracing search projects around the United States, which I'm going to talk about in the next lecture. We have a Texas Supernova Search Project. There's a big one in California. There's a big one operated by Harvard University, basically based out in Hawaii. So with all these projects, we discovered right now we have about 60 to 70 of these events. So we can start talking about statistics, and we can start looking at trends when you have a significant number of data. And obviously, the first data point that defines this category of supernova is their high peak luminosity. So in terms of brightness, their luminosity exceeds minus 21 magnitudes, which means that the peak luminosity of these events is minus 21 or below, minus 22, minus 23, which means even brighter. Now, they're also very diverse. So they are their own zoo within the general zoo of supernovae. There is no superluminous supernova that looks exactly the same or very similar like another superluminous supernova. Some of them are hydrogen poor, some of them are hydrogen rich. The evolution of their light curves, as you might have seen from the previous slide, shows nothing in uniform. Some brighten up really fast within 10 days. Some take a longer time, like 70 days to reach peak luminosity. Some decline very slowly, while others decline very rapidly. So both in terms of light curve and spectra, those are extremely diverse events. Yet another clue to what is going on here. It's a very interesting event. Now, obviously, the reason we discovered them with the Texas Supernova Search Project is because we were not biased. We were looking at the entire sky. And that goes back to the fact that the host environment, the host galaxies for these superluminous supernova tend to be low metallicity, which means that they have a low content in iron and elements above helium. That's what we mean by metals in astrophysics. It's not, when we say metals in astrophysics, we mean any element heavier than helium. So the only non-metals are basically hydrogen and helium. Everything else, silicon, calcium, we term as metal. And those were low metallicity, which means they were young and not bright galaxies, dwarf galaxies. And obviously, they're also very rare. We, even with the fastest and the most technologically advanced search project, we only discovered 1 to 5 or so events. Now it's increased a little bit over the last couple of years, but on average, 1 to 5 events per year. So those are rare, They tend to live in low, dim galaxies. They're very diverse and they're very bright. And this is, I think, a very nice plot from my colleague Avishai Galgal from 2012, which shows how the light years of these superluminous supernova events compare with the light years of typical supernova. So if you remember the discussion that we've done about the zoo of supernova explosions, we have supernova type 2, type 1As, hydrogen-rich, hydrogen-poor, 1BCs, and so on and so forth. All of these are down here, the plateaus, and most superluminous supernova, at least peak luminosity above -21. Look at these beasts right here. Not even type 1A, which are the brightest usually, come close to superluminous supernovae. So the red, the magenta, and the blue line are some superluminous events we found. So very, very bright. And they're also very diverse in terms of their composition. One thing I emphasized before is that spectral is the single most important observation we do in optical astronomy, not just optical, but in general optical astronomy, because it gives us a lot of hints about the nature, the physics, the nature of these events, in terms of what temperature they have, how hot they are, what the conditions are, and of course what the composition is. And a lot of these events do not show any sign of hydrogen at all in the spectrum. They're deprived of hydrogen. So those are called superluminous 1, type 1, to keep in accord with the original terminology for regular supernovae. Those are the hydrogen-poor superluminous supernovae. And then there's some that show very prominent lines of hydrogen. So those are those very strong lines in the spectra, especially H-alpha and H-beta a little less, but H-alpha is a very prominent feature. And it corresponds to the emission of hydrogen. And those have a lot of hydrogen, those don't. It's very clear. And also, they have hydrogen in emission. So this is an emission line versus an absorption line which goes down in flights. Which means something is triggering, something is inducing this hydrogen emission. Very important clue here. And I'm going to talk about what it possibly could be. So, hydrogen-rich and hydrogen-poor. Now this is where I'm going to go to the hard stuff, to the physics, and to the hypothesis that we have, the scenario that we have about what the nature is of superluminous supernova. Personally, I've contributed a lot over the last 7 years of my career on that model, as well as the next one I'm going to discuss, the PAIR-INSTABILITY supernova model, which I'm going to analyze for you guys. But this is my favorite, and this remains the favorite for a lot of us in the community. Because it all goes back to this image of complex nebulae and complex geometries around stars. You know, stars are, it's not just you have a bright, beautiful star in a clean environment. The star itself is going to lose matter. And sometimes it's going to be within a very complicated structure, a very complicated cloud, a nebula. And the supernova is going to inevitably interact with this environment. So this is what this model is about. The model suggests that superluminous supernova occur from the violent interaction between the supernova ejecta, the debris of the star itself, with mass around it, with circumstellar material around it. And when this collision takes place, there is very energetic and very powerful blast waves, or shock waves, as we say in physics, that transfers both the circumstellar material and the stellar material, depositing energy. And this energy deposited by the shocks, imagine those shocks kind of like a nuclear blast wave. And this shock deposits energy. This blast wave deposits energy, which then converts into luminosity. And this is where you get this extreme brightness from. It's conversion between the kinetic energy of the shock to luminosity. And I'm not going to discuss, so this is a very complicated model people have made to try to fit what we see in the light years. I'm not going to go into detail of that, but I'm just going to tell you that we can fit superluminous supernova characteristics. We can actually reproduce the light years that we see, the behavior that we see, the diversity between the light years that we see, if we assume a model like that. Now, a model like that will have a lot of free parameters, right? I mean, stars will have different masses. They're not all going to have the same mass. Circumstellar materials, the shells around stars, with which the supernova collide, are going to also have different masses, different densities. They're going to be at different distances. And guess what? The universe is 3D. They're also going to have different geometries. So you have so many parameters, which is not, when you see something so diverse in nature, nature is not just, you know, reducing Sometimes it's very convenient to reduce everything to one or two dominant parameters, but sometimes it's harder. Nature has a lot of parameters, and a lot of parameters involved in the physical configuration will give rise to big observed diversity. So the power of this circumstellar model, which is something we observe, the diversity of circumstellar environments around massive stars, is that it naturally explains the diversity of supernova in terms of light years. Supernova 2006 GY is one of the most, also discovered by the Texas Supernova Search Project, is one of the most well-studied supernova ever. We managed to discover it very early on as supernova was rising in brightness up to the maximum, which got to about 60, 70 days, and then we followed it for another 150 days. So we have 200 days worth of, and now more than a year actually, we kept following after that blood came, there's more data points right now. So we have more than a year of observations of this event. It's a very well-studied event. We have a lot of spectra. We know the composition. It was hydrogen rich. We saw hydrogen for this one. And it had this, the fact that it was slowly, it took like so long to reach the peak luminosity. If you remember from my lecture about light years, that means that there was a lot of mass associated with it. Light took a long time to diffuse out of this mass. It took 70 days. That means there was a lot of mass interfering between the source of light in the center of a supernova and the free escape to space. And the red line right here, I'm not going to go into technical details, but the circles are the observations. This is what you see with your telescope. And the red and the dashed line are models we make. Models we make, and this is not even a computer model. This is not even a numerical simulation model. This is a model we produced. I led this research in 2012. It's a pen and paper. You just put the basic physics down. If you remember, I showed you a really long formula when I was talking about light years. The biggest formula I'm ever going to show you in this lecture series. That's the model I'm plotting right here, effectively. But adding to that the contributions of the interaction. Because the model I showed you only had the nickel giving energy. In this case, you have the nickel radioactively decaying, but you also have on top of that this blast wave from the interaction that causes energy. And this is what you get when you do simple models like that. That took me less than 20 seconds to run in my laptop. And you get an idea of the general properties of this event. And you see that it's very massive. It comes from a very massive star. The shell around it has to also be extremely massive, like 1 to 10 solar masses of material. So you got 50 to 60 solar mass of material colliding with another 10 solar mass of material. We're talking about the massive collision, massive cosmic collision. This is what these are, massive cosmic collisions. It's basically the star colliding with its own axis. And we see, someone can also do more complicated, more accurate numerical simulations. So you can take the complicated physics that describes how light propagates through matter and solve for all of that in a one-dimensional or three-dimensional model, and you will get this numerical light years. And if you compare those two, you will figure out what kind of circumstellar material properties you need to explain the supernova. But we can also do the same thing for spectra. So one thing that I showed you before, when I was looking at spectra, is this prominent H-alpha emission line. So if we're going to describe this supernovae, we have to be able, using that model of circumstellar interaction, to reproduce this very, very fundamental feature that's associated with it, which means that O6GY had hydrogen. And this is what we've done here with models. Models reproduce the observed behavior. This is the happiest moment in the life of a theoretical astrophysicist, is when your model produces you something that looks like your observations. And then you're happy. You can say, I understand what's going on now. I have a better idea of the last 2 months of my life actually were put in good use. So this is an example of how models look like, models of spectra interacting with supernova look like, with this very prominent feature right here corresponding to hydrogen. And how is this feature produced? Well, first of all, you need hydrogen, because that's a hydrogen feature, self-explanatory. But what happens is that the supernova ejecta colliding with the circumstellar material, which is made up of hydrogen, you have this blast wave moving into this hydrogen material. Now, hydrogen is made up of atoms, and it's made up of hydrogen atoms. There's a proton and an electron going around the proton. Very simple. It's very simple configuration. Now, if you give it enough heat and enough energy, the electron is going to be detached from the proton. That's when we say the hydrogen is ionized. The electron is detached from the photon. Now, once the shock goes through, that's exactly what it does. It's so energetic and so hot that it detaches the electrons from the photon. So it ionizes the hydrogen. But then the shock moves forward, keeps moving forward. And then the material that was right behind the shock eventually cools off after some time. So the electrons go back to their protons. And that's called recombination. And when that happens, this is a quantum property, but when it happens, that emits light. And it emits light in a certain frequency, which is what you see in this line. This line represents exactly that. It represents the fact that this hydrogen cooled off, recombined, and produced these photons, this special frequency, producing the feature we call H-alpha, hydrogen alpha. Okay, we can have this very complicated model to explain very accurately the hydrogen-rich supernova supernova, because we see the spectra, we can explain the spectra, we can explain the light curves. How would this model be relevant to a hydrogen-poor superluminous supernova where we don't see hydrogen? It turns out that over the last 60 or 70 superluminous supernovae we have right now, the majority of them turn out to be hydrogen-poor. So then we have a problem. We have to figure out a way to make this model relevant for a hydrogen-poor situation. And one of the most well-studied examples of hydrogen-poor supernova was discovered in 2007. Supernova 2007 BI. And again, this is something my colleague Alisai Galgan worked on. We discovered at the Texas Supernova Search Project, and this is actually the only supernova-related paper that has the two first authors being Greek, George Luminous and myself. Kind of proud about that. So we discovered a similar one in 2006, but they published the one in 2007 before us. And that was a very well-studied hydrogen-poor event. There were no hydrogen-rich features in the spectra. But the other problem about it was that they discovered it a little bit before light reached maximum luminosity. You know what the problem with that is, right? When your light curve is not well constrained. You don't see the entire evolution of light. You just see going to peak and then going down. You're missing some data before that happened. Well, that makes it hard to constrain exactly when the explosion did happen. It's like having a curve like that and missing all the data points. Then did it happen here? Did it happen here? Did it start here? So it's really hard to say when the explosion took place. And because of that reason, it's hard to deduce an accurate measure for how much mass was involved in the explosion. Because mass is related to how long it takes for light to get to peak luminosity. And if you don't exactly know how long that takes, you don't have an accurate measure of mass. So people were starting to be a little suspicious. Like, okay, this is very bright, but can this be very bright if there's just this little mass involved? Or how much mass needs to be involved with the explosion for this to be so bright? So there were estimates ranging anywhere from 20 solar masses to 120 solar masses. So it was totally unconstrained. So that was another problem with it. But we did have good spectra. And the model I proposed with my supervisor, Craig Wheeler, back then was, wait a second, guys. We see circumstellar action being relevant all across the hydrogen-rich world. What would make it non-relevant to the hydrogen-poor world? Well, all you need to think about is you could have situations where stars that have long lost their hydrogen envelopes will eventually lose their helium or maybe a little bit of their carbon oxygen envelope, and you will have circumstellar action between material that's not hydrogen-rich. So it's a similar principle to type 1b, type 1c supernova that I described before, in which case you had binary mass transfer removing mass from one of the stars, depriving it of hydrogen. In this case, you're going to have other mechanism, which is one of the mechanisms we have proposed, which I'm going to touch on a little later, is the one of pulsational PAIR-INSTABILITY supernova. In other words, to put it simply, this is a mechanism that removes mass from the outer material from the star in the form of pulses. So the star does this. and pulsar material. It's dynamical, it's not stable. The entire style is not stable, and the effect of this instability is to remove the outer layers in a series of injection events. And this way you can remove hydrogen. You can remove a lot of hydrogen, you can even remove helium. You can be left over with a core, a carbon-oxygen core of the star. And eventually, if that happens, you will have a situation where you have a carbon-oxygen core star, deprived of hydrogen, colliding with either helium or carbon-oxygen circumstellar material. And that means there wouldn't be any hydrogen to be seen in the spectrum. So this is the model we proposed, and we actually were able to fit light years of hydrogen-poor events with this model. Now, one of the biggest challenges, because it's a very tough physics problem, because the more you go up in atomic mass, it's easy to figure out hydrogen and helium, but when you start looking into the lines and the properties of carbon, oxygen, silicon, the physics become a bit more complicated, and to reproduce those features in a model takes more work. So now what we're working on currently is not just explaining the light rate, which we've done, but also explaining the spectra of hydrogen-poor superluminous supernova. And that will put the nail in the coffin. This is what I'm working on right now. This is one of my major research projects. So, and this is exactly what this slide conveys what I talked about. The challenge of spectral modeling is hydrogen-poor superluminous supernova using the circumstellar interaction model. And people can make the claim that I just made, that it's just not there, that's why you don't see it. Or there's other complicated physics that would hide it from you. That maybe hydrogen is actually there, but there's intervening material, or there's other scattering effects going on that would block this line from being seen. And that's why you don't see it. But to answer that question, you have to do the full physics. You have to put it in a computer, you have to solve for the radiation transfer, for these complicated lines. And that's tricky business. That's what we're trying to do right now. So, to summarize on my favorite and one of the most popular models for superluminous supernova, the circumstellar interaction model, I always like to show the image of Eta Carina right here, because that showcases the diversity and the complexity associated with massive stars. It's not just a bright spot most of the time. It's surrounded by this really complicated, massive material that inevitably going to interact with. And that will play a role how it looks like, and how bright it's going to be, and what the properties of the spectra are going to be. So this model seems to check all the major observational characteristics associated with superluminous supernovae. It can reproduce the high peak luminosity. It can reproduce the diversity. We do know that very massive stars, like this one, this is a very massive star, Eta Carina, lose mass episodically before they become supernova explosions, so it can reproduce that. It's in agreement with that fact, and they're very rare, because if you remember the example I gave in the first lecture with the pebbles in the beach, the more you go up in the size of the rock, the rarer the rocks are. There's more small rocks and sand grains than there are bigger rocks in the beach. Kind of like the same thing with the stars. There's 95% of the stars out there are like our sun, more or less. They're not massive. So there's only a few of the 1% that are massive enough to produce these features, and are massive enough to produce superluminous supernova. And that also seems to be in accord with that. Again, remember what reality looks like. And this is a nice GIF image. One of my favorite images in astrophysics. This is another model that we discussed, and also I've published on the order of 4 papers in this. It's an exotic type of explosion that's nothing like core collapse or nothing like type 1A supernovae. The technical name for it is PAIR-INSTABILITY supernova. And I'm going to explain to you very simply how it works and what it is. So, I've talked about core collapse supernova coming from massive stars of the order of 15, 20, 25 times the mass of the sun. Now imagine you have an even more massive star. That's why it's so exotic. 100 solar masses, 120, 200. Take the sun and multiply by 200. Those are giant stars. And they're there. They're out there. We found them. We've seen the most massive star we've observed is 280 to 300 solar masses. That's the most massive observed. So they're there. They're very rare. Okay? But imagine you have one of these stars. It's going to evolve. You remember my first lecture was about stellar evolution, how stars evolve. So it's going to start fusing hydrogen. First of all, one thing you can take out of the table outright is it's going to have a short life. It's really massive. It's going to consume its fuel more aggressively than other less massive stars will. So those stars only live for 1 or 2 million years, while our sun is going to live for 10 billion years in total. So those are very short-lived stars too. Okay? Now, it's going to burn hydrogen to helium. It's going to make a helium core. And then it's going to start fusing helium to carbon and oxygen. And then you're going to have a carbon and oxygen core surrounded sometimes by the helium and hydrogen. The onion structure, okay? But when that happens, for these stars, the stars are in a very weird location in terms of their physical conditions in the core. They're in a place where the density of the core is relatively low, yet the temperature is very high. Temperature is in excess of 1 billion degrees. It's very high, 2 billion degrees. Whereas the density is about 10 to 100,000 times more dense than the water in the ocean, which in astrophysical terms, it's not that dense. Okay? So that is a very unique physical condition in thermodynamics, which allows matter in this condition to rapidly produce pairs of electron and positron. So electron, as you all know, is a fundamental particle with a negative charge. Positron is the antiparticle of the electron with positive charge. Same mass, positive charge. And those particles are created and they are annihilated all the time. But by doing this, by having this process occur in the center of that star, the pressure that would go to support the star against gravity, because let's not forget, the reason stars shine in the first place is the balance between gravity that tries to pull inwards and the internal pressure tries to expand it. But then you're going to start, and what supplies the internal pressure? The photons, the light that's produced by the nuclear reactions in the center of the star. Now, if you start having those particles becoming these electron-positron pairs, becoming more and more and more and more and more frequent, you will start removing this light that was going to go to support the star from collapsing, because it's going to be absorbed by these particles. So by doing this, what you do effectively is you reduce the pressure inside the core of the star. What happens if you reduce the pressure? The gravity wins. The star starts to collapse. What happens when the core of the star, which is made out of carbon and oxygen, starts to collapse? Temperatures go up very, very rapidly, densities go up very rapidly, and you start to explosively burn carbon and oxygen. So you have carbon and oxygen, now you're hot enough to just burn it really explosively and produce immense amount of nickel. Talking about 1 to 10 to 50 solar masses of nickel. So once you have this amount of radioactivity powering your explosion, then you can make something really bright. You have 50 solar masses of nickel, you can make something really bright. This is exactly how this PAIR-INSTABILITY supernova work. This is kind of like a famous plot of stellar evolution. It kind of shows how different, how stars with different initial masses evolved to the end of their lives. And you can see that, low mass stars like white dwarfs, like our sun will make white dwarfs. A little more massive stars will make neutron stars and black holes. And this is the region, this is the narrow region here where PAIR-INSTABILITY supernova take place between around 140, almost 300 solar masses. Stars that start with this mass are guaranteed to die about this really violent explosion. Now, let me make a point here and say that not all PAIR-INSTABILITY supernovae are going to be bright. The ones that produce most nickel are going to be bright. And the ones that produce most nickel are the ones that tend to be the highest initial mass. So, although some stars down here will explode as PAIR-INSTABILITY supernova, some 120, 150 solar mass stars, they will make 1 or 2 solar masses of nickel, which is a lot. However, the light that they produce from a radioactive nickel decay will have to diffuse out from a giant envelope. So you're going to lose a lot of that light. It's going to be diminished a lot by the time it escapes. You have to go through 100 solar masses of envelope. So those will be dim. Although you make a lot of nickel, you will be dim because your light that you're making is absorbed by the mass. But the more you are increasing the effect of nickel, the more you can create superluminous supernova. So you need really massive stars. So this is one of the problems of this model for superluminous supernova. You need really, really massive stars to do this. It's not that they're not there, it's that they're very rare. They're rare enough to not explain the already rare occurrence rate for superluminous supernova. And I mean, this is just a movie. I talked about MESA, stellar evolution code, that we're using to evolve stars from birth to pre-supernova in astrophysics. This is just a movie from MESA. It just shows, this is the temperature and the density structure of the star. This is the prohibited area. Think about this red line here. This is where the area, when the star goes into that area, this is the star creeping in. This is the core of the star, and as you go out, it's the, the envelope of the star. But this is it looks kind of like a snake. It's creeping into that area. Once it gets in there, it's going to blow up as a PAIR-INSTABILITY supernova. So most stars never get into that regime. Most stars are out here. But the more massive you are, the more you are doomed to cross this limit, this red line, which will mean that you'll explode as a PAIR-INSTABILITY supernova. And this is an example of a MESA stellar evolution calculation of one of these events. And you can see that a lot of these zones here are getting, right here, they're getting into the red regime. And this is the point of no return. So what we do is we do this with MESA, we get up to that point, and then we map this model into a code like Flash that can do the hydrodynamics and the nucleosynthesis and can produce all the radioactive materials. And let me move forward. And what I've done, I mean, this is one of my most cited papers in 2012 with my supervisor. What I've done is try to understand what the effects of rotation to that, because a lot of massive stars we observe are actually very rapidly rotating, and that's going to change a lot about the evolution. And this turns out to help the PAIR-INSTABILITY, the case for the PAIR-INSTABILITY supernova model as related to superluminous supernova. Because the more you rotate, the less mass you need. That's our main result. I'm not going to get into the specifics, but the more you rotate, the less mass you need to get into that regime and blow up as a PAIR-INSTABILITY supernova. So if you were non-rotating, you would need, say, 200 solar masses. But if you're rotating fast enough, you could go down to 120, 110 solar masses. So it makes it easier because there's more lower mass stars out there than higher mass stars. So this is one of our highlight papers that just basically look at that. And of course, we've done the explosion with flash, and this is what you see here. On the left, you see the star collapsing and then exploding, and on the right, you see the density. And those contours represent nickel. Look how much nickel we produce. It's mixed out, and it has this weird mushroom-like shape as the stellar material expands. So this is how this PAIR-INSTABILITY supernova explosion looks like when you simulate it with the flash code that I've done. This is for a 200 solar mass initial star involved with MESA. Okay. And I'm not going to spend a lot of time on that slide. This is just going to the fact that, hey, if you have rotation, how does that change the light rate and the spectra? It turns out it doesn't make a much of a difference. It does change the mass limits, which is important, but it doesn't change what you're going to see out of your telescope too much. Those light curves and those spectra, regardless of if you're rotating or non-rotating, they look pretty much the same. So the key takeaway point from this is that one, just by looking at the PAIR-INSTABILITY supernova explosion, cannot really tell whether the star was rotating or was magnetic or was of low metallicity. Now the question, a lot of discussion took place back in a World Conference in 2013, whether that hydrogen-poor supernova 07BI could actually be the first PAIR-INSTABILITY supernova discovered. And there was the discovery team, Galliano, was pushing for it, and others, including myself, were saying, wait a second, you can do this with something different. You can do this with circumstellar interaction. The truth is, if you just look at the light curve of 07BI, which is shown here with those data points in the upper left panel, and then you just try to fit this light curve with models of PAIR-INSTABILITY supernovae, which is what those dashed and dotted lines are, you get a pretty good approximation. You can have a 100 solar mass star that's going to hydrogen pool that's going to give you a PAIR-INSTABILITY supernova that's going to give you the same behavior of the light. However, what we've done is like, okay, remember, spectra is truth. We got to reproduce the spectra too. The light curve is not good enough. And when you try to do this, and we use a very special code to do this, a Phoenix code with my collaborator Gunnar Rostrom, it turns out that the spectra do not match at all. There's a mismatch, which means that there's a problem with this model. You can't really explain 07BI as a PAIR-INSTABILITY supernova because you cannot reproduce the spectral properties of this event. So, scoreboard for the PAIR-INSTABILITY supernova model as related to superluminous supernovae. It cannot explain diversity because there are not that diverse events. It's just nickel that controls how bright they are, and the light curve, nothing controls how the light curve is going to drop or is going to decline. It can explain sort of like the occurrence rate because they're supposed to be very rare. However, if you include rotation, that turns out not to be the case, so that becomes an X because you have more massive stars that can become very slow supernova rotation. And it can explain the host environment because the lower, so it turns out metallicity, and when I say metallicity, I mean elements above hydrogen helium, have an increased mass loss from stars. So if you have a star, a massive star, that is higher content of metals than another star, it's going to lose mass more effectively. There's a correlation there. It turns out that those galaxies where we find those superluminous supernovae are low metallicity, which means that they would reduce the effect of mass loss, therefore allowing for more massive stars to be present. So some people say that as a clue, oh yeah, you know, the reason that you have this host environment that are low metallicity might help to form PAIR-INSTABILITY supernova. Now I should mention that this also goes back to how important those are for early universe studies. Because when the universe was formed, there were no metals, right? There were hydrogen and helium. So the first stars that were formed did not have, they had to make their own metals, and they didn't make a lot. And then most of these stars were also predicted to be really massive from simulations. So we're pretty sure that the first cosmic explosions, alongside with gamma-ray bursts, which I talked about the other lecture, are PAIR-INSTABILITY supernova. Because you could make that massive star, it didn't have a lot of metals, you wouldn't lose a lot of mass along its life. So you could successfully create PAIR-INSTABILITY in the early universe. And we are going to be looking for them when the new James Webb Space Telescope comes online. It's going to be one of the key projects, which is going to be like 10 times more strong than Hubble. And one of the key projects for James Webb JWST will be to look for this primordial PAIR-INSTABILITY supernova explosion. And then there's a third alternative that people are discussing. It's a very interesting, cute model. You can have massive stars that, if they're rotating out and if they have strong magnetic fields, they will produce, their cores will produce magnetars, so highly magnetized pulsars that rotate in a really high frequency. Under certain conditions this happens, and the main conditions is rotation of magnetic fields. Not all stars are. So that's the argument they use to explain the rarity of these events. Well, you know, not many stars rotate that fast and have that many magnetic fields and are that massive. So you need a combination of three to have this engine to power superluminous supernova. But the ones that do can reduce this magnetar that spins down and converts its magnetic energy, rotational energy into light, which then can brighten the supernova up to really high luminosities. And you can make simple analytical models of how do you expect the light to evolve out of that power mechanism. And you can fit some superluminous light waves. This is an example here, where supernova 08ES and the one that people were discussing as the PAIR-INSTABILITY supernova 07PI can actually be fit by MAGNETAR SPIN.DOWN model. So this is a very interesting model. It could be relevant to a lot of these events. We still have problems trying to fit the spectra with this model. We can fit the light curves, but there's a question because the emission you get out of these magnetars is non-thermal. It's synchrotron emission. And there's a big question whether that emission thermalizes the ejecta. This is a very complicated radiative transfer problem, and people are still trying to approach it. Under certain conditions, you should be able to do it. So, you know, there is hope for this model, actually. It's a very interesting suggestion. Or at least some of the superluminous supernova could be related to this mechanism. So yeah, this is the scoreboard for this MAGNETAR model. You need rotating and rapidly rotating massive stars to do this. You can explain peak luminosities that you see in superluminous supernova, and you can explain the occurrence rates. Now there's still questions whether you can explain the reason why they all tend to be associated with low metallicity host environments. And the diversity, it turns out that with this model you can fit a lot of light curves, but you can't quite fit the entire diversity of light curves. There is some superluminous supernova that do crazy things in the light curves, but you can in no way fit with a model like that. And there's another question that I raised very often. What stops rotation and magnetic fields if this seems to be relevant to hydrogen-poor superluminous supernova a lot, right? So the question I raised in conference is that what stops high rotational magnetic fields being relevant to hydrogen-rich superluminous supernovae. You know, why you cannot invoke such a model to explain hydrogen-rich superluminous supernovae? And the answer initially would be, yes, you can, but then you look at the spectra of hydrogen-rich superluminous supernovae, and you see this very prominent emission line, which is it's a definite sign of a blast wave moving through matter. So when you see that line, when you see this narrow emission hydrogen line, you know that there is circumstellar action, because this is produced as a result of a shock moving into hydrogen matter. So how do you reconcile the two, and why would magnetars be preferential towards one category versus the other? So there's still a lot of room for discussion, but it's certainly a promising and very interesting model. So to summarize, the reason we discovered this exceptional type of event, superluminous supernova, is because we entered the era of unbiased transient search projects, where we weren't just targeting, we weren't doing pencil searches, targeting specific galaxies, but we looked at the entire sky using small telescopes with a wide field of view simultaneously. And that's what we found from the University of Texas in 2005, this incredible phenomenon. And they're very rare. They seem to be associated with galaxies that are very, very low metallicity and very dim, dwarf, as we say, dwarf galaxies. They're very diverse. They're diverse in the way the light curve evolves. They're diverse in the spectral characteristics, and that was one of the key things we wanted to investigate. And this combination of observational characteristics stirred a lot of interest and discussion in my community. And I happened to become a graduate student when this was, boom, it was right there in front of me. So it was a lot of luck, because I'm like, oh yeah, I can make a career out of that. So there you go. And this has been my favorite puppy, you know, over the last 7 years. And it turns out that there's 3 models that provide some sort of explanation of why those supernovae are significantly more luminous than everything else. And the 3 competing models are the one that I'm siding with most of the time. It's circumstellar interaction, the fact that stars do not die in clean environments. They lose mass, and they will interact with this mass at some point. And this mass can be anything. It can have any geometry, it can have any composition. This naturally explains diversity. And there is a PAIR-INSTABILITY supernova model that requires a really high, very massive star. It's quite likely, but it still has its shortcomings. And there is this MAGNETAR SPIN.DOWN model that I just talked about. And those superluminous supernova are going to be important over the next 10 years in early universe studies. When JWC and WFIRST come along, we'll be looking out for these events at the edge of the observable universe. Thank you very much. Yes?
I have 2 questions. First one is, is there any possible association between typical events of high luminosity SNs happening in low luminosity dwarf galaxies, and then the CSM, the high mass of the CSM, the circumstellar matter surrounding these kind of stars, any kind of association? If it's low luminosity, these galaxies, maybe I'm thinking that the mass, the increased mass of the circumstellar matter has something to do with that.
Yeah, people have, that's a very good question actually. People have looked into correlations between host galaxy metallicity and type of superluminous supernova or mass loss implications. It turns out that you will suppress mass loss in a low metallicity dwarf galaxy, but it doesn't seem to be a strong correlation. So we just maybe don't have enough data to answer that question completely, but so far it points in the direction that, yeah, we can even find hydrogen-rich events in dwarf galaxies.
In dwarf galaxies. Yeah. And also, is this James Webb telescope, is that what is supposed to be built in Hawaii on that volcano?
No. James Webb is actually, it's a funny story. It's one of the most initially underpriced projects in astrophysical history. It's going to be an orbital observatory. It's kind of like Hubble. So it's going to be sent into orbit. It's going to be about 10 times stronger and more sensitive than Hubble is.
Wow.
But initially it was priced at about 1.5 billion, and that was not a good estimate. It turns out to cost 5 billion. So, you know, we're glad it's still going to happen, because there were a lot of discussion about how to get funding. Next. Yes?
I was going to ask you, all these stars and models and modules you talk about, do you have any classification or model that puts them in order of discoveries or ages or anything, any type of classification model for them?
For the models, or?
Yeah, for the stars or the supernova or whatever.
Well, classification is actually happening in 2 steps. So those really rapid telescopes, the robotic telescopes that find them, they have algorithms installed in them, smart algorithms, smart computer programs, that can tell you very fast, by comparing to a larger data set, can tell you what type this might be, based on the first 2 data points. So that's the first step into the classification. Once you get a hint from that, of what's going on, then the final classification happens when you turn on the bigger telescopes and you take spectra. And you can say, oh, this has hydrogen, this doesn't have hydrogen. So this is how we observationally classify supernovae. In terms of the models, there's no particular classification. There's just 3 models, 3 engines are seen feasible in the context of stellar evolution as we know it. That can be relevant to what we see. So it's just the 3 different proposed techniques. Yes? Anything else? Yes, sir.
Astrophysicists confuse people when they talk about heavy metals, anything beyond helium.
Right.
So in your low metallosity dim galaxies, dwarf galaxies, does that apply that there's very little material beyond the
Exactly.
helium?
Exactly. So if you were to compare the ratio of materials heavier than hydrogen, than helium, that you see in those galaxies, with the ratio that you see in our galaxy, for example, it would be much lower. So it's a comparative kind of thing. We set the stage, we set the bar at Milky Way galaxy. We say this is solar metallicity. And then we compare this metallicity with other galaxies. We say how much lower metal content this galaxy has versus this galaxy versus this galaxy. Next. Yes, sir.
One more question. Is there a difference between the data transfer and the 2 types of data transfer? Does that make a difference in terms of yielding the...
I'm sorry?
The type of data transfer, analyzing the data transfer, is that for the radioactive decay, does that make a difference?
Well, no, I mean, there's, so that's actually a good question. You know, if you're going to have PAIR-INSTABILITY supernovae powering these events, you have to have a lot of radioactive material, like needles, for example. Which means that if you go at very, very late times, you should see the decline rate of the light curve being consistent with what you expect from nickel, which is pretty standard. Turns out for 99% or 95% of these events, they're not consistent with that decline. That's another problem for the PAIR-INSTABILITY supernova scenario. But there's a few that is consistent. That doesn't mean that you couldn't reproduce it with another model. It just happens to be consistent with these errors. So beta decays and radioactive decays help us in the sense that they're pretty standard in the way they decline. So, any other question? Yes, sir.
I'm looking at this picture of Eta Carina.
Yeah.
Is it because that's how the matter was ejected during the explosion, or is it how it was distributed in the surrounding?
Very, very good question. I love talking about that. So, Eta Carina has this bipolar. Actually, let me just put the picture up for everybody to see. Eta Carina has this very characteristic bipolar structure. So there's a really bright source here, and then there's 2 lobes at opposite directions. The question was that he's asking, how is that came to be, basically? So why do you have this configuration? There has been two models on that. The first model that I'm aware of was that of a massive star that underwent an instability, a pulse, a really strong pulse, that ejected material. The reason that material is not distributed spherically around it is because, the explanation is because this star is really rapidly rotating. And if you're rapidly rotating, you tend to have a preferential direction how you eject material. So that's, but then when people did a very careful geometrical study of the angle of these lobes and how they evolve, turns out you need a really, really high rotation. Not impossible, but really high rotation to produce this. Now the most accepted theory about how this came to be is that of binary interaction. So instead of just having one massive star here, you might have a massive star and another star, which you can't really see because material here is really dense. And we haven't been able to penetrate deep enough to see the individual stars, if there are two of them. And they're so close to each other, there's such a close binary that you can't practically separate the two. So the theory is that you could have a 60 solar mass and a 40 solar mass star really tightly together. And this binary interaction, this spiraling together, can produce outflows that have this shape. So if one of the stars loses mass, it's going to be deformed as it expands because of this binary interaction. That's the most popular model for why this looks like that. But you still have massive stars in the center. Next. All right, thank you all very much. I'm happy